Hey there. Okay, so I'd like to introduce a new unit, the electron volt. It is usually written as EV, and even we call it EV. Not very many people say electron volts, but the unit EV is actually really important in physics, and I think now is a good time to introduce it because the parallel plate capacitor is a really great example of how we came across this unit. Now, at first, it might seem like a unit of potential, and that would, I guess, kind of make sense. This is actually a unit of energy, okay? So you can compare it to a joule. Now let me give you the conversion first, so that you'll know what to do with it, and then explain why. The conversion is that 1.602 times 10 to the negative 19 joules is equal to 1 electron volt. Now this number, hopefully, is a pretty familiar one to you by this point. There is a reason that we have this conversion. So what we would like to do is take our parallel plate capacitor that we've used so far, attach a battery to it, and we get to determine what that voltage is. So let's make this a 1 volt battery. Well, according to what we've learned so far, that means that if this red plate is going to be at 1 potential and equal potential, that is exactly 1 volt higher than the potential of the negative plate, then we know that there's going to be a linear scale in between. So if we were to graph this out, that we had electrical potential on the vertical axis and position on the horizontal axis, then what we can see here is that if we get the full distance, then we're at the distance d. If we're halfway there, we have it written as half d. And we have the potential that would be between the plates, right? So if we take our line, it's going to be at 0 volts here at the negative plate, and it's going to be at 1 volt here at the positive plate. Typically, we call the negative plate of a parallel plate capacitor the 0 volt plate. Again, we always get to choose where the reference point is for voltage, so yeah, it's just sort of a standard. It's what people have always done, right? So that way, if the negative plate is 0 volts, or the negative terminal of the battery is 0 volts, then that means that the positive plate and the positive terminal will both be at positive 1 volts, or positive 6 volts, or positive 9 volts, or whatever it is that they happen to be, right? Okay. Now, it doesn't have to be this way. It could be that we put a 2 volt battery, and if we did, then we should erase that. We put 2 volts here instead of 1 volt, and that would lead us to a same linear relationship, but by the time we got to plate D, we would have achieved 2 volts of potential from the negative plate to the positive plate. Notice that that means that in this case, the 1 volt is halfway in between the plates, right? Halfway in between the plates is always going to be at half the voltage, right? And to every linear place in between, right? Now what we want to do in order to understand why we have this unit conversion is we have a negatively charged plate here. It turns out if you heat up that plate, those electrons, like we said before, they're pretty mobile. So if you heat up the plate, then one of those electrons it's released from the plate. It's going to be repelled by that negative plate, and it's going to be attracted by that positive plate, or you could say it's going to want to ride backward on that E field, right? And so it's going to be accelerated. Now, what you can do, and this is really cool, is you can place a little hole in your positive plate here, so that when that happens, some of those electrons will slam into the plate, but some of them will come shooting out the other side here at some velocity. So we might decide we want to know what that velocity is, or we could say, velocity is a little bit of a sloppy term for us when we're dealing with energetics, so why not just call it kinetic energy? I mean, we all know what the mass of an electron is anyway. So what kinetic energy is going to come out of that hole? What electron is going to come out with what kinetic energy? We get to put whatever voltage we want on here, so let's go ahead and just put 1 volt and see what happens. If we release a negative charge at the negative plate, then I want you to consider what that means. This negative charge, when it's released, is going to be accelerated from a point of 0 potential to a point of 1 volt, and it's going to go out that hole and then maintain, because there's no field outside of this parallel plate capacitor, it's going to maintain whatever kinetic energy it achieved by the time it got to the positive plate. Can we figure out what that is? Absolutely we can. Why not? We know a conservation of energy now, right? So if we were to take a look at the energy of this situation, we might say, well, what's the voltage initial? It's 0. What's the voltage final? What's the charge of an electron? Well, it's negative E, right? So where E is 1.602 times 10 to the negative 19, right? Coulombs. So if we look at the initial energy, the initial kinetic energy is 0, and the initial potential energy is also 0. So because the voltage is 0 initially. And so in total, we start off with 0 energy, and then by the time the electron gets to the positive plate, let's take a look at our energy. It's going to be negative E, 1.6 times 10 to the negative 19 coulombs, times the voltage, whatever that is, voltage final, right? In our case, it's 1 volt. And so we could go ahead and put a 1 in front of here, right? Let's go ahead and put a 1. So 1 times the charge of an electron times 1 volt, right? Okay. And, oh, actually, I should, if that's going to be 1 volt, then I should get rid of the caps on my V there. Let's get rid of those. Because it's a unit, not a variable at this point, right? There we go. All right, so that's going to be the potential energy, and then we add the kinetic energy. Well, we said we're not that concerned with the speed at the moment. We just wanted to ask what the kinetic energy was. Well, what is the kinetic energy? Guess what? It is 1.602 times 10 to the negative 19 joules. And if you were to multiply this volt times the charge in coulombs, you would get it in joules. But instead of multiplying by coulombs, we're just multiplying by E, the fundamental charge. And when we do that, it becomes part of the unit. So that is an electron volt. Electron volts are actually quite useful in a lot of areas of physics. We're going to be running into them a lot when we get to optics, and also they're super useful in quantum mechanics. So it's good to understand what they are. Okay, let's take a look at, really quickly, what that means for a electron that has been accelerated through 1,000 volts of potential. What kind of kinetic energy would you expect it to have? See, the thing that's very useful about this is we don't have to go through a really big calculation to know what we would expect that to be for an electron that is accelerated through 1,000 volts of potential. It would be 1,000 eV. That's the kinetic energy that we would expect it to have. So the voltage leads directly to the kinetic energy in that case. Okay, value of the electron volt. Now, for more clarity on a lot of this, make sure that you explore your labs carefully, and also make sure to ask me lots of questions, and also try your quiz videos. And don't forget to read your book.